Okay, hello everyone. Thanks for coming. Um, MySpace, Dropbox, LinkedIn, all of these big companies, big websites, they all have one thing in common. At some point, all of them suffered from losing their customer passwords data. And what does it tell us? Well, it tells us one thing. If such big players, big companies had such problems, uh, every little service, every application that we work in, we build, we create, can also suffer the same problem. So what can we do to protect ourselves anyway for such an unlikely event of losing password hashes? Well, the purpose of this talk is to show you that slow hashing algorithms are the way to go. They're very useful for such situation, and they are specifically designed to protect our hashes the best way possible, the best way available now. Just out of curiosity, how many of you have heard anything about slow hashing algorithms? If I raise a hand. Okay, a couple of people. That's pretty much the usual percentage, pretty low. So that's pretty good. I hope even though you know something about slow hashing algorithms, you'll still benefit from this talk. All right. So the usual stuff. I think you're already familiar with Slido. Please use Slido for questions. I will try to answer them after the talk. Choose room 10. This is the room we're in. All right. A couple of things about me. I have a name, I have an email, and I have a job. Right. So straight to the agenda. Basically, it will consist of two parts. First part will be like a more theoretical part about slow hashing algorithms, what they do, how they work, a little bit about this, and some times comparison. And the second part is the actual case study that we did a migration of password hashes in www.ocado.com, and I'll run you through the process and tell you about the problems that we had, tell you the plan, everything, and the summary. Okay, let's start. So hashing algorithms. I'm pretty sure every single one of you have come across something like, for example, MD5, right? So this is an algorithm that takes data and computes a one-way hash and produces a result. So this is a simple result for hashing a string of GeeCON 2019. And we have a hash and a result. It's a one-way hash, as I said. So the only way, there is no easy way to see what was the input value for it. The only way to check whether a specific hash is a specific value is to hash a value and see if the hashes are equal as the specifics of hashing. All right, but what are the types of hashing algorithms that we can that we have? One group is are these fast, old school, and general purpose algorithms, and you know them. Those are MD5, SHA-1, and so on. And these are cool, and these are really easy to use, and we know how to use them. But a couple of characteristics of them they're not designed specifically for strings, which we would like them to be because we are dealing with passwords, and also they're good for binary data, and also they're very fast. So this is a nice feature when you like to quickly compute a hash, for example, to see whether the download that you did from a page is a valid download. You just compute a hash of a big binary file quickly, and you can say, okay, that's the file that I needed. So this is their purpose. And the second group are slow hashing algorithms, also known as bcrypt and friends, and these are the examples of the algorithms. I will talk briefly about every single one of them in a moment, but I just want to say that the order in which they are presented and the order in which I'll talk about them is actually not coincidental. It's the exact order in which OWASP, the security organization, recommends them to use. But every single one of them is good enough. Every single one of them is tried in the field, and tried in production, and it's working. Okay, so we know what kind of hashing algorithms we have. Okay, so what are the characteristics of slow hashing algorithms? What are they designed for? So they are designed to slow attacker down. So in the unlikely event that we had lost our password hashes database, the only way for an attacker to know the passwords is to brute force them. The brute force, like he probably has a database of some example passwords, or he or she is computing them, and it takes time, right? So they're the slow hashing algorithms are specifically designed to slow the attacker down. They are also providing secure hashes with salt. Are you familiar with the salt concept? Anyone? Raise your hands. Right, yeah, most of you. So salt is something that we add to a password before hashing it, just for two reasons really. If it was only a hash of simply a password and a hash, then attacker could have prepared some kind of already computed hashes of passwords that he knows, and it will be even quicker for him. So providing a salt which will randomize the result is good, and also using different salt for same password produces a different hash. So even if we have all passwords are same, we have different hashes. So it also slows attacker down. And the third thing, very important, is that these slow hashing algorithms need to be reasonably configured. And what I mean by that is every single one of them has a notion of a cost parameter, and we are in charge of that. And we provide a cost parameter for a slow hashing algorithm to say how slow it should be. What slow means, I will explain a little bit later. All right. So Argon 2. Why is this a yawning baby here? Well, it's yawning probably because I'm boring, but it's a baby because Argon 2 is actually the new kid on the block, the newest of all of these algorithms. In 2013, there was something called a password migration contest held, where people could submit a new hashing algorithms, and there was a committee of very intelligent people who, in 2015, 2 years later, announced that the winner of this competition, password hashing competition, is Argon 2, and this is currently recommended as the best algorithm available. Although in this world, 2015 is really kind of yesterday. So some people are reluctant to use it and want to shift to some of the algorithms that are older. But it's a official recommendation to use it. The second algorithm is named very nicely, and what image here shows is an actual name of a railway station in Wales. I think that the creators of this algorithm knew about that and they wanted, the copy. So the name of the algorithm is PBKDF2, and it's of course it's an acronym because this is IT. Hello, and it stands for password-based key derivation function 2, because version 1 was not good enough. What about this algorithm? Well, this algorithm is actually it is configured by a number of iterations of an underlying function. So, for example, you can provide to this algorithm that you would like to use SHA-256 underneath, and you would like to do 500,000 iterations. And this is what this algorithm accepts. It does the work, and it provides a result. That's how it works. And also, it's an interesting algorithm because it has something that is called FIPS certification, which is a Federal Information Processing Standard. And if you work in a kind of an industry like banking, which requires specific certifications, It's an US certification that you could probably require. So this is a good way to go. This is a good algorithm as well. Another one is script. Script is a specific algorithm. Well, it's all of the other algorithms. They are focused on core, on the CPU core. And creators of script thought that maybe memory is something that is a little bit more expensive, a little bit harder to get for a potential hacker, let's say. So they made it that there is a possibility in script to use memory instead of CPU cores, and make it memory intense, memory hard. So this is the specifics of script. And the last one, but not least, is bcrypt. Bcrypt is actually, from what I know, the first algorithm. Around 1999 it was created. So if you didn't feel old, you should. And this is the image shows a blowfish, because actually bcrypt is using blowfish cipher underneath, and it is configured by the power of 2. So if you configure it with a 5, it will do 2 to the power of 5 iterations of blowfish in the background. Yeah, that's so these are the algorithms. All right. So I would like to show you now an example of a bcrypt hash, how it looks like. So let's hash a random string with bcrypt, and this is what we get. This is one of the possibilities that the hash can look like. This is an OpenBSD hash format, which is designed not only for bcrypt but for other ones. This is the one of the possibilities we can get a hash, and I will go through the elements just for a moment, just to tell you what they say. So the first element after a $, which is separator, is a version. So OpenBSD format is something more general. So 1 is for MD5 and 2 is for bcrypt, and it was 2 for bcrypt, but first version had a bug. From what I know, it had bug with around UTF and ASCII. So they created a 2A version. And if you're interested in the topic, there are also 2X and 2Y versions. A very interesting lecture. So I recommend it. And so this is basically saying this is a bcrypt hash. Next, there is a separator of $1 and 08. The 2 digits that actually provide you the number of 2. So this is the cost factor of the algorithm. So this hash, to produce this hash, you need to do a 2 to the power of 8 iterations of blowfish, and it's 256, and you'll get the result. Next, you have a separator, and you have a 22-character salt encoded in the hash. And this would be easy if it was base 64. It's radix 64, which is a slight modification of base 64. Again, you can read into it just for your information. And the last part is actually the hash, the resulting hash, also encoded in radix 64. So this is the hash. From my perspective, it's a pretty clever way to create a hash and to present it. I think it's good to know. So okay, we've covered the bcrypt hash. And now I'd like to show you a live demo of code to compare hashing speed of some algorithms. So let me just change the screen to IntelliJ. Can you see everything? Hope it's visible. Okay. So what's here? Actually, we will do 10 iterations of every of these algorithms. And MD5 bcrypt with the cost factor of 8, 10, and 12. And we will see how much hashes can we do in a second on my machine, and also see the hashes. So let's run the code. Let it compute. Will take some time. Right. Okay. So firstly, MD5. MD5 it's always the same hash. In bcrypt we have different hashes. Does anyone know why? Yeah, sure. The very good answer. Yeah, the salt is every time the salt is different for bcrypt, and for MD5 there's actually no salt. And you can of course generate salt on your own. I was just trying to show you that slow hashing algorithms have salt in their definition. So you have to provide salt for them to work, and they encourage you to create a random salt. And for MD5 or all these other ones, you need to remember about it. So this is the difference. And okay, let's compare the times. So almost 1,400 MD5 hashes per second for bcrypt with a cost factor of 840. With a cost factor of 1014 and with a cost factor of 12.3. So I think it shows what slow really means and why these algorithms differ from the ordinary ones that we know and use on a daily basis. But this is on my computer, right? Usually, if we are dealing with a hacker that is like professionally doing stuff, the hacker will have some kind of a different machine, right? So I found an article in the interwebs. It is a blog post. And the date of the article is over a year old now. This guy used $5,000 to build he called it a budget cracking rig. Well, it was budget for him. I don't know how about you, but let's say it's a budget cracking rig, okay? It's $5,000. I think it's, let's say, affordable for some. He used the benchmark hashcat version 3.2. Which actually is a useful benchmark to compare different hashing algorithms, right? I think he got interesting results. For MD5, he got a result of 19 billion hashes per GPU per second. He had 4 GPUs, so multiply that by 4, and this is the result of this cracking. Almost 80 billion hashes per second to be computed using GPU power. So that's astonishing for me, really. Secondly, SHA-1. Okay, this is a little bit slower, but not that slow. It's like 3 times slower than MD5, but still, a lot of hashes can be computed in a second on one GPU. The most interesting part is one of the slow hashing algorithms, bcrypt. So bcrypt with a cost factor of 5, which is 32 iterations of Blowfish, is not even 11,000 hashes per second. And to be honest, the cost factor of 5 is really low for today's standards. We can go higher, we can go slower. So I think this speaks to people's minds that, you know, this slow means slow. Okay, so let's forget about, no, I may not forget about, let's switch from the theory to practice. So now I will tell you a little bit about the migration process that we did. So how did we actually strengthen our hashes in our database? How did we strengthen them, and what was the process? What was the plan? So just a little bit of information about Ocado to know where we are. We do a lot of stuff, but what we actually will speak about is this part is the online shop. So there is also, you know, some routing, some warehouse stuff that we have, AI, automatics, robotics, but now we'll focus on this part, the website that has customer data, over 700,000 customers we serve. So a pretty big service, right? So what was the before state, before we even really considered changing anything? Okay, so our application already used the slow hashing algorithm, already used bcrypt with a cost factor of 8, which may seem enough, right? Well, I'll get back to it in a second. Some old customers still had MD5. It doesn't mean that they had pure MD5 hashes in the database. It just means that in the old days, in the beginnings, we used, in the very early years, we used MD5 for hashing, but there already was one migration process held, And what we did with the old MD5 hashes, we actually hashed them again. So we took the MD5 hashes of all customers, and to strengthen, we just run bcrypt through it. And the obvious thing is that for a new customer, if new customer registers or a customer changes password, we're transferring this to bcrypt because we know what the password is. But for the people who didn't log in yet, we have this MD5 password hash type. So this is how the part of the table looked like, and this is an example of a customer that is, let's say, an old customer, and we store the password hash type as MD5 in the database just to say to the application that is gonna compute the hash, then when this customer wants to verify his password, we'll firstly compute MD5 hash of it and then compute bcrypt. And then we'll just compare it with the value that we have in the database. For this customer, it's easier. It's only, we just get the password, we compute a bcrypt hash and compare it. And that's the way it goes. All right. So this is what we had. So why did we decide to change? Everything looked pretty much solid, pretty much okay. One thing, we have an information security team, and at some point they asked us, hey, could you please revisit the way you're storing passwords and see if there is any improvement that you can take, just to make it safer for our customers, to make it more secure. So this is one thing, and so we did some benchmarks, and it turned out that bcrypt with a cost factor of 8 took around 80 milliseconds to compute. It's fairly fast, really, from the UX perspective, from user point of view. That's not really a thing, right? So we did a comparison of different cost factors and how much did it took to compute a hash. So looking at the results, we decided, well, the cost factor of 12 with not even a half a second of wait is something that users won't even bother having, and it makes us safer, it makes our hashes stronger, but still we're not losing the UX. We're not using the user experience. So it looked cool. And we thought, maybe how about just increasing the cost factor of bcrypt? But recently, when we were starting considering the migration, there was an application security team created in our company. So we decided these guys seem like the right people to ask for an advice, or if they want to have any input in it, or maybe some clever ideas. So we did. So we said, hey, listen, we have this problem. Information security wants us to revisit. What do you think? Can we do something cool, something good? And they said, well, this is a perfect example of for work for our team, so we will help us. And how did they help us? So they created this lib called crypto, or extended it with some functionalities. So they have created something called a PasswordHasher that takes care of, surprise, surprise, password hashing. And a useful interface that I will talk in detail a bit later, which underneath uses well-known cryptography implementation, like, for example, Bouncy Castle. And at this point, I need to strongly advise you not to ever implement crypto on your own. It just never ends well. There are good people who do it, and we should trust them. We should use trusted, well-known, and checked implementations, right? So Bouncy Castle is one of the examples. And PasswordHasher produces a hash vector that acts as a password hash, and I will also dig a little bit deeper into this to show you what are the cool features of it. So once we decide to go with hashing using a password hasher in our application, it's since then, it is controlled by application security. We don't need to bother changing the parameters because they will only tell us there's a new cryptolib version, just upgrade it and you have the features, right? Pure profit. Right. So I told you that there is this hashVector which acts as a password hash, and this is an example of a hashVector, and I will go through the elements to tell you what they represent. So the hashVector is basically telling the algorithm, telling us what steps to take to compute a hash. So this hashVector means that first element is required to do an MD5 hash. Then there is a separator, and this is a base 64 encoded salt for this hash. So all right, we have a password, we use this salt, we append this salt, we do an MD5, and what else? There's a separator of algorithms, and there's another hasher that we should use. So we take this hash that we already computed, and we run it through bcrypt. The next part you already know. This is actually the input parameters for bcrypt, so a number of iterations in salt. And there's another separator. And there's another algorithm that we should use. So we take the bcrypt hash and we run it through pbkdf2. And there's a separator, and then it tells us use SHA-256. This is an input argument for pbkdf2. Then there's another separator, and it tells you, okay, it's 250,000 iterations that you should do. And then there is salt encoded, right? So there's a separator, and this is the last part, and that's actually the resulting hash. So after all these operations that we did, we take the value that we got and we compare it with this, and then we know whether it's a good password or not. Pretty cool. Right. So this is the API that they proposed and that we are using. A couple of methods, and I will go into a single one of them to say what they do. So the first one is the simplest, so it's just hash. So you provide a plain text password from customer, and you just have a hashVector in the result. So you can see that in this example it provides the pbkdf2. That's why it's because that application security decided to go with the pbkdf2 as the main algorithm, as the best algorithm for now, and they decided that this is the one that we should use. We trust them. This is application security, so this is how it goes. We're using pbkdf2. All right, so we hashed. That's an easy part. Next method is very useful when for example, customer logs in, right? And we need to check whether the password is valid or not, whether it's correct. So this is pretty straightforward. We provide a password and a hashVector, which is probably taken from a database, and we get verification result as a result. But this is a pretty smart structure that we get in the result, because it has two fields. Is success is obvious, true or false? And the get hashVector is actually another method that can be null if the will of course be null if the success is false. But if success is true, it may not be null, and if it's not null, it means that there is a better, shorter hashVector that we can replace it in a database. So let's say algorithm changed, the number of iterations is increased, whatever, we just already have it computed because we provided the plain text password. So when PasswordHashes decides that this is a correct password and it has the password in plain text, it already computes the shortest hashVector for our use. So very convenient. And the last step is actually for the migration process. Is very useful. So it accepts already a hashVector. So this is a precondition that whatever hash you have in your database, you have to translate it to hashVector for PasswordHasher to understand it. But then you can provide it, and it will just add the strongest element in the end. So in this case, pbkdf2. So the strongest algorithm will be there. So actually will be that strong as the last algorithm here, and will be cool. So very useful API. All right, so it seemed like we had everything in place, so we needed to create a plan for this migration, and how we approached it. So what would be the first thing that you would do in such situation when you would like to strengthen password hashes? What would be the first step? Like when to change the hash? Any ideas? User signs in, right? User signs in, user logs in. That's the easiest thing. So we then can verify that the password hash is correct, and you can change it to a different hash because we have a plain text password. When a customer creates and changes password, we can also migrate the hash because we also have the plain text password. So this is this situation, but we cannot really rely on a situation where 700,000 customers log in, and then we're ended the migration, right? It will take forever. Some of the customers may not log in that often. So we would like to do something in the background as well, just to speed up the process and make it secure. So we came up with some asynchronous background jobs. The first one is actually translating the existing hashes to hashVector. As I already said, for the password hasher to use the migrate method, you need to provide a hashVector. So you need to translate the existing hash to a form that password hasher understands. So this is the first step. Not changing the way they are calculated, only changing the language, let's say, to hashVector for password hasher to act. And the next thing is actually upgrading hashVectors. So using this migrate method, adding the last step, the strongest step of PBKDF2 is the second job that we came up with. And the last step that's actually crucial to all the process is a cleanup, because we are as secure as our weakest hash. If we had left the old hashes in the database, had the new ones that were strong but had the old ones, we actually are still in the same place as we were in the beginning. So cleanup is crucial. All right, so this is the plan. About migrating password when customers provide them. So let's go through this process, how it works. Okay, customer provides password, easy stuff, web form, username, password, right? We're computing the old type hash. We're acting on old type hash, checking whether it matches or not. An obvious part, if it doesn't, error. If it does, we compute hashVector because we know we have the plain text password. We store it in the database, and in a case of a password change or creation or user registration, we also need to store and modify the old hash. And this is also very important. This is because we absolutely need to have backout possibility. If anything goes wrong with our release, we just absolutely need the possibility to go back to the old hashes, and they need to be updated. We don't want to just put customers through the process of resetting passwords or anything else. We don't want them to feel anything bad. So this is important. All right. As far as the first of the asynchronous background job is concerned, translation, right? So we're starting with something like that. Password hash and password hash type are the old columns. We added 2 new ones. hashVector for surprise, surprise, hashVector, and migration status, which helps us control the process. So we added hashVector of null to every single record, and we added a migration status of none to every single record. And then the translation job takes next password, next password, next password, and does the translation. So it's basically operation on strings, really, because we don't have the plain text password. We only derive the parameters for password hasher to compute a hash. So we translate the existing hash that we have to hashVector. In this case, we have MD5, let's say MD5 customer. So firstly, we need to MD5 hash it, then we need to bcrypt, and then we have the result, right? In the situation when we have only bcrypt, it's easier. It's just bcrypt hasher and that's it. The hashVector is shorter. And we set the migration status to translate it, okay? The next step is upgrade. Is upgrading to the strongest algorithm PBKDF2, right? So for the MD5, we run the, for every password, we run the migrate method of PasswordHasher, and it appends the PBKDF2 hasher element to the hashVector, and we have a secure, stronger hash. And we set the migration status to migrated. The same happens for bcrypt, the same happens for MD5 customers. Considerably. So we have an updated hashes, and after full migration is done, as I said, very important part, we lose the old data. After we are sure that our new code works and it's fine, we need to lose the data because, as I said, we are as secure as our weakest hash. So we need to get rid of the weakest hashes, and I will play that again because it took me like half an hour to do this. Right, so the full migration is done. And then also a handy thing that we came up with before we run the migration, or when we were testing it, it turned out that we would like to have an overall status of it. So we generated some kind of a report. As you can see, I'm a perfect front-end developer and UX designer in one person. So this is a crafted table. It says which passwords are in which status and the number of records, so we can say, yeah, where are we with the process. But it also has this failure counter, which is telling us that something went wrong. It may be every possible exception that we run into, we're logging it, and we can check. Okay, we should check the logs or anything. So this was useful for us. All right, and I wouldn't be true if I missed this part. This part is the ugly stuff, the problems that we had. So okay, let's dig in. What were the problems? First thing, the time taken to migrate. So before we did it, we did some calculations. How much will it take us to, just to do the full migration of our database? Okay, so we did some computations. Translating password hashes. Okay, I have an upgrading password hashes. 30 days. All right. So this is actually a whole month of continuous work of a computer. It's pretty long. And so we didn't know if we could affect it anyway. So okay, so we decided that something like this is heavy on a CPU, right? So we wouldn't want an application node to be less performant during this process. And given that we had the on-prem deployment, we decided to maybe create another node which will be disconnected from the load balancer, and this node could do the work but not serve traffic to the customer. So it was the same application, but just not doing the actual, not serving the traffic. And this application did the work in the background. So we tackle it this way. And after completing the migration, we actually connected this new node to the load balancer. We had one node more because the algorithm is a little bit stronger, is a little bit longer. So just to have a bigger speed. That's what we did. All right. So that was one problem. Another problem: orphan password entries. So in the process of testing, fortunately, it turned out that we had some passwords that don't really have owners, and it was surprising. So we thought, okay, we will not start it before we find the problem. Why is that? So we have a process that in production, test environment as well, every now and then registers new customer, logs in customer, just to do a smoke test, just to check whether everything works, right? So after it finishes the registration, it deletes the customer from the database because we don't want to have this data. So this part of code was lacking one important line. Delete password. Okay, so fortunately we identified the problem. So the easiest thing to do was to delete the orphans. Firstly, to prepare a bug fix, deploy it, delete orphans, and for some time just monitor if the orphans don't appear, and we're good to go. But this is enterprise, this is IT. What if, okay, we say these passwords don't have owners. What if they do? We don't know why, but what if they do? You know how it is, right? So we would like to have a backup, right? We would like to have a backup plan. Okay, so let's contact the DBAs and see how it works, how the backup works. So it turns out that backup, of course, is possible. We have backups, but it will take a lot of resources to actually bring up the backup in the case of situation where something is wrong. So we said we cannot afford this really, because we have running business, we have an online shop, we have a website, and we don't want customers to wait. Oh, you cannot log in really right now because stuff happens. No, so we decided, okay, we will do a backup on our own. We actually created a clone of the table. We moved all the orphan passwords there, deleted them from the original table, kept the schema same. And after some time, when we were sure that the fix was okay and we don't have any orphan passwords, we just deleted them. So this is how we approach this. Right. Another problem. So entire process took over a year. Very long time. But why really? When I'm saying entire process, I'm telling you that from the very, very beginning, when someone said, okay, please revisit the way you're hashing passwords. So all these discussions, all these plans, all this talking, all this preparation of API tests and stuff, all of it is included in this time. Also, at some point when we started the migration, there were some problems with the performance of the site. And the team that was investigating it found out that there is some background process going on, and maybe it's slowing it down. They didn't know, maybe it's slowing down the whole application. So they asked us to pause it. We've paused it. It was in this process. They also covered it very, very nicely and very speedy, but it was another thing that slowed us down in total, right? So that's why it was over a year to complete it. Okay, so I'm almost done. Summary. There's things I would like you to remember after this talk, the key takeaways, I think. So, all right. First of all, I hope I convinced you that slow hashing algorithms are the way to deal with passwords. Just please use them. The thing is that you need to monitor time to take into compute hash and reconfigure if needed. I mean, the computational power increases with time, right? And we all know it. So every now and then, if you have, if your application is keeping password hashes, it would be really cool for you to check if we're okay with the time that there is. Maybe we can increase it. Maybe we can slow potential attacker down again and more. If you're dealing with an existing situation, existing service, existing application, the hash migration is a little bit complicated. It's not obvious, but it's not impossible for sure. We did it, and we're happy with the results. And it's very important to prepare yourselves to properly test it and identify all the loose ends if there are any. Probably there will be a couple of them. And very, 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 very important stuff, clean up afterwards. So after you're sure that everything works and everything's okay, just clean up after the process. And of course, you need to monitor to see whether during this process, the migration process, we're all right. Everything works fine. Right. A couple of links. You can use some OWASP storage, password storage cheat sheet, how to store passwords, the link to a password hashing competition, and so on. Also very cool. Have I been pwned website. I don't know if you're familiar with it, but it provides a lot of resources to see whether your email or passwords has been compromised if in any of the data breaches that happen around the world. Right. So thank you for listening, and I'll be happy to answer questions. So I guess Slido now, right? Okay. Right. So first question, should I pass password to hashing function as a string or char array? Yeah, I know about this, that basically if someone runs to gets access to our running code, running application, that it is possible to derive password from the string that we have. It's harder to get a char array, and we actually did some approach for that and consider it. I would say that it's a good practice, but it's not very easy to do. And actually, if you have, I would say that if you have all the other security stuff done, you can then go with this. But I would not treat it as the most important thing to do. I hope that answers the question. And here, no. Okay. I think that's the same question really about the char array or byte array. Okay, does combining encrypt algorithms might they make the password even harder to decrypt? Yeah, right. When you look at the overall times that each of the steps take, it's actually the last one is the strongest one, the most time consuming, and I would actually stick with this because it is simpler. We're actually like the 99% of the security comes from the last step. So combining it sounds a bit to me like security by obscurity. So I would not go with this approach because we'll have this long tail of hashing algorithms that we need to go to run through, and really I don't see the benefit from it, because we just can increase the number of iterations of algorithm, and that's it, and that we already have safer. And then I don't know if that answers it or not. Okay, I don't hear no. What if someone combines his own crypto with other well-known? Yeah, that's the problem with. I would still say that own crypto is dangerous for me a little bit, because that it's not a coincidence that all of these algorithms, there's version 2, there's version 2a, and there are really deep mines into the industry. And I would say, of course you can try, but I wouldn't do it. It's your decision. I wouldn't recommend it. Okay, slow hashing algorithms can make DOS attacks possible. How do you prevent? Yeah, so right, of course, because it takes a lot of time to compute them. Right, so this is really something that I believe infrastructure should take care of. So if we have some IPs that we are attacking, that we are being attacked, a lot of requests, or a pattern that we can see, it's just limiting the request number. It's most of this, I believe, should be on an infrastructure side. Some of it we can do on our own in the application side as well. So we can do some some recognition of IPs on our side, let's say if infrastructure is not capable of doing it, and just after a couple of requests, like for example, we can limit the number of requests for a specific login, right? Because we can store it like in a separate database. We can store login and the number of attempts for a login, and like block it for 10 minutes after five attempts that happened in a short time. For example, we can do that. We can do IP checking also on the application side. I strongly believe that infrastructure can do something good on their own. We can help as well on the application side. Okay, anonymous hacker, nice. Thank you all for listening, for coming. Hope you'll enjoy the rest of the conference. Thanks.